Hello, and welcome to my presentation on biodegradable mulching films. My name is Adam Buckley, and my colleagues on this project are Sarah Landrum and Jonathan Sizemore. This project seeks to address an environmental concern, which is the use of low-density polyethylene films in agriculture. Low-density polyethylene films are typically subjected to improper disposal where these materials persist and only serve to pollute natural environments and ecosystems. A feasible alternative would be one in which disposal were eliminated altogether through the development of a film synthesized using biodegradable materials that decompose naturally in ambient conditions and promote soil and plant health in the process. Low-density polyethylene films are non-biodegradable in natural environmental conditions and are produced using fossil fuels which are in limited supply and causes pollution on a large scale. Recycling of these materials is labor-intensive and costly. Due to the costly nature of disposal, agricultural industries are choosing to cut corners and save money through cheaper disposal methods. Because of this, illegal dumping and burning of low-density polyethylene films are chosen instead of disposing of these films through proper channels. These biodegradable mulching films will be designed using biocompatible materials that have no adverse effects on soil or crop health and introduces intrinsic fertilization to the soil to promote the health of future crops. This film will last the entirety of a crop cycle, slowly degrade under hydrolytic conditions over time, and re-enter the soil where it will be converted into biomass and gases. Any persisting remnants of the film can be tilled into the ground where it will be fully degraded. Ideally, these films will begin hydrolytic degradation through the introduction of water. The film must also show durability to natural weathering and maintain mechanical integrity in hot, humid conditions. Materials for this project had to meet design constraints stipulated in the initial design concepts. The film had to degrade in ambient conditions after the crop cycle, prevent light from passing through to inhibit weed growth, and promote soil health through intrinsic fertilization. 20,000 molecular weight polyethylene glycol diglycidyl ether is a commonly used cross-linking additive that can be seen being utilized in many environmental applications. Soy protein isolate is a food-grade protein that will aid in adding fertilization to the soil. Carbon black is used to add pigment to the film, which will prevent light from passing through, and lysine will be used as a cross-linking agent. Additionally, chicken feathers will also be used as a binding agent for the biodegradable mulching film. Previous formulations included 6,000 molecular weight polyethylene glycol and soy protein isolate. A variation of mixture ratios were synthesized by dissolving polyethylene glycol and soy protein isolate in water at 70 degrees Celsius for approximately 20 to 30 minutes. Once the constituents were dissolved, they were then placed in an oven to dehydrate off any residual water in the mixture. Once the mixture was dried, it was then formed into a film shape using a melt press. It was concluded that this formulation produced films that demonstrated too much brittleness and very little to no flexibility. Esterification between polyethylene glycol and soy protein isolate was also crucial to the development of this film. Water was hypothesized to be a strong enough acid to initiate esterification processes, but it was later realized that no esterification was taking place and that a blend of materials was being produced instead. Future formulations will introduce a strong acid or base to help promote the esterification process. Polyethylene glycol diglycidyl ether, soy protein isolate with carbon black and lysine as a crosslinker proved to be a conducive formulation for producing flexible films. Flexibility was retained after drying and melt pressing, and the pigment provided a good color barrier to keep light from passing through. Chicken feathers were also added to the film. The purpose of the chicken feathers is to act as a binder in the film. Review of literature showed that common binders and plasticizers, such as wood cellulose particles and nanofibers, could be used to impart mechanical strength to the film. Future analysis and degradation studies will be administered to the film to ensure that the film will perform as needed under prescribed conditions. These conditions will mimic natural degradation seen from typical environmental weathering. TGA will be used to establish the onset of degradation of the film. It is important to know at what temperature the film will start to break down and lose its mechanical integrity. DSC will be used to establish different properties of the film, such as glass transition and crystalline melting temperatures and heat capacity. DMA will provide insight into the durability of the film under mechanical stressing, and QUV accelerated weathering will be used to mimic environmental conditions for degradation. The combined data from the analysis techniques will offer insight into how well our biodegradable films will perform under typical usage. Formulations for these films is subject to change to meet the stipulation conditions of the design. A major concern through the entirety of the development of biodegradable films has been the cost of polyethylene glycol diglycidyl ether versus traditional low-density polyethylene. Low-density polyethylene is a cheap commodity polymer that can be found in most hardware and home and gardening stores, making it readily available at a cheap price. An efficient and cheap synthesis method will have to be developed if polyethylene glycol diglycidyl ether and soy protein isolate films are to replace low-density polyethylene in large-scale agricultural operations. Low-density polyethylene has an average cost of $0.05 per gram versus polyethylene glycol diglycidyl ether, which has an average cost of $0.2 per gram. This difference in cost makes it difficult for polyethylene glycol diglycidyl ether to compete with low-density polyethylene. Low-density polyethylene has seen so much use in the industry that it has solidified itself in common applications. Our hope is to provide a potential alternative that will promote environmental health and give incentive for agricultural industries to switch to more modern solutions. A shift in thinking will be required to adopt this alternative, and concern for our environment should be a top priority. It is our goal to produce materials that parallel these environmental concerns and serve as a remedy for pollution. With costs set aside, it is our belief that polyethylene glycol diglycidyl ether and soy protein isolate films with lysine and chicken feathers will be an adequate substitution for non-biodegradable films. Though the initial development has only seen small-scale synthesis in laboratory settings, hopefully this film will see future iterations that transfer well to large-scale productions. Thank you for your time. Thank you for listening to my presentation, and if you have any questions, I would be very happy to answer them.